Okay, thank you. All right, so today what we're going to do is we're going to talk about neighboring optimal control. Now, the idea is this. So I'm going to simplify the problem a little bit, not much, but just a little bit, which is that suppose we have the following optimal control problem. So we want to minimize j, which is equal to phi, but now I'm just going to consider it to be a function of x of tf because I don't want to get into all the t0 and tf stuff. Just unnecessarily complicates what it is I'm trying to do here. So the cost function has a Mayer term and a Lagrange term, and then there's a set of constraints, dynamic constraints, that have this form. And then you have an initial condition that x at t0 equals x0. So I'm not dealing with path constraints, and I'm not dealing with things that are explicit functions of time. It's not necessary for the purpose of what I'm doing here. And you'll see why in just a minute. So suppose that x star of t, u star of t, and lambda star of t is an optimal solution. So we know that if I evaluate, I'm going to let the following things happen. I'm going to say x of t, which is a general trajectory, is equal to x star of t plus delta x of t. And then u of t is equal to u star of t plus delta u of t. And then lambda of t is equal to lambda star of t plus delta lambda of t. Okay, so I haven't done anything yet. I've just done a perturbation. These quantities, delta x, delta u, and delta lambda, are what are called neighboring trajectories. All right? So I'm assuming that I have an optimal solution. I perturb that optimal solution by some amount. And you can see that if my initial condition, x of t0 is equal to x0, then what that tells you is it tells you that delta x of t0 has to equal delta x0, where that's the perturbation from the value. Because if I perturb the entire trajectory, I'm not forcing the boundary conditions to be satisfied, all right? I'm saying that the whole trajectory can be perturbed. So that includes the initial point. The initial point can be off from the value for which the reference was solved. So the reference was solved, over here, and I got an optimal solution. But when I perturb it, I'm perturbing the whole thing. All right? Now, suppose now that we look at the cost function. So we know, and I'll just do this, that the cost is given as. So I'm just going to look at it as a function of the state. Clearly it's a function of more than the state. That was a function of the control and stuff. But I'll just do this because it's easier to do it this way, and then the rest of it falls in place, as we move along. So what I'm going to do now, though, is I'm not going to hold this to just first order. I'm going to hold it to second order. So I know that this is equal to j of x star of t plus the variation in j of x star of t, and then plus the second variation, x star of t. Now, I'll define what these things are in just a minute. You remember when we derived the first order optimality conditions for an optimal control problem, we set the first variation equal to 0. So we found the necessary conditions for optimality by setting the first variation equal to 0. So if I'm evaluating this on the optimal solution, this is going to be 0, right? It has to be 0 because that's a necessary condition that it be 0. So let's deal with the second variation. Okay, we have to deal with that. But before I deal with the second variation, I need to do a small aside here, which is that suppose that g, which is a scalar function, is a scalar function. This is a static function. It's not a function of time. G of z is a scalar function of the vector z. Okay, so it's a static vector. So I know that, and suppose, and let z equal z star, which is the minimum of this function z, plus delta z. Notice I use a little big delta here. I'm not using a little delta because this is not a trajectory. It's a static quantity. So I know that g of z star plus delta z is equal to g of z star plus the partial of g with respect to z evaluated at z star times delta z plus delta z transpose times the second partial with respect to z evaluated at z star times delta z plus dot, 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 higher order terms. So let's suppose we only hold the second order. Holding only the second order, we have g of z star plus delta z is approximately g of z star plus the partial of g with respect to z evaluated at z star times delta z plus delta z transpose times the second partial evaluated at z star times delta z. Now, what do you know has to be true in the case of a function? If I'm minimizing a function, the necessary condition is that this has to be 0, right? So on the optimal solution, it has to be 0. So you can see that the trajectory here, the function here, if I perturb it away from the optimal value, it's going to equal whatever the cost is at the optimal value plus this this term over here, which involves the second derivative. So in a similar manner, we're going to go through and we're going to do the cost exactly the same way. We're going to use this result, and we're going to do it for these for the trajectories over here, which basically we have this optimal solution. We're perturbing away from this optimal solution to find a neighboring optimal solution, and we know that the first variation in the cost functional is 0, which leaves us with the second variation. So we need to figure out what the second variation is. So we have to go through the math and figure out the second variation. So if you look at the second variation, so this is the second variation now in the cost functional. The second variation in the cost functional is we have to now hold to the second derivatives of all of these quantities here. So what we're going to get is if I take the second derivative of that first quantity, I'm going to get a 1/2 delta x at TF times phi xx evaluated on the optimal solution times, there's a transpose, times delta x at TF. That holds the second derivative. That holds the terms to second order in this. And then I have to then do the same thing with the integral. Now I'm just assuming here that T0 and TF are fixed. So I'm not doing any perturbations there. So what I'm going to get is I'm going to get delta x transpose, delta u transpose, times LXX, LUX, make sure I do this in the right order. LXU, LUX, LUU, times delta x, delta u, dt, and these are all evaluated on the optimal solution. So if you do that for the cost. Now we're going to do the same thing for the dynamics. Next, we know that x dot is equal to x star dot plus delta x dot, right? Approximately. So we're linearizing this. And we also know that x dot equals f of x and u, which is equal to f of x star plus delta x u star plus delta u, which is equal to f of x star u star, vectors, plus, now we're going to take the partial, I'm only holding this to first order, the partial of f with respect to x evaluated on the optimal solution times delta x plus the partial of f with respect to u, again evaluated on the optimal solution times delta u. So if I plug this in up here, I know that this is approximately equal to x dot star plus delta x dot. But I know that x dot star is equal to f of x star u star, so these two things wind up canceling out, which gives me that delta x dot is equal to the partial of f with respect to x evaluated on the optimal solution times delta x plus the partial of f with respect to u evaluated on the optimal solution times delta u. Now suppose, just for simplicity, I define these as f of t and g of t. Then I get those dynamics right there. So those are the linearized dynamics. So what I've done is I've approximated the cost functional with a quadratic, which is sitting here. And the reason I have to approximate with a quadratic is because the first variation is 0 on the optimal solution, right? So I can't hold the linear terms, because the linear terms are all 0 at the optimal solution, because I'm evaluating all these things at the optimal solution. So I have to hold things to second derivatives. So the next thing I'm going to do is to make some more notational things here. So I have all these notes, which is that suppose now that we let that we define a bunch of things. P f is equal to phi xx evaluated at the optimal value. So this really is the same thing as saying partial second phi partial x second evaluated at x star at tf. It's the final value. And I'm also going to make some other substitutions here. Q of t is going to equal Lxx star. M of t is going to equal Lxu star. And then R of t is going to equal Luu star. So if we do that, then the second variation in the cost looks like this, is that delta squared j is going to equal 1/2 delta x transpose at tf times pf times delta x at tf plus 1/2 the integral from t0 to tf delta x transpose delta u transpose times q of t m of t m transpose of t r of t times delta x delta u dt. And the dynamics are, again, delta x dot is equal to f of t delta x plus g of t delta u, and the initial condition delta x at t0 is equal to delta x0. All right? Now, suppose we want to solve that optimal control problem, okay? So this is an optimal control problem, right? Where I've perturbed away, and what I want to do is, given some perturbation in the initial condition, and given these linearized dynamics, I want to minimize the cost subject to these constraints here. So this in itself gives me another optimal control problem to solve. This problem is what's classically known as a neighboring optimal control problem. So this whole thing is a neighboring optimal control problem. Now, it does not, it seems like, you should just be able to do this, right? But you can't just you can't just do this because it's you have a you have to solve this problem because you've got to linearize to get and then take the quadratic approximation to get all these functions. And now you've got this perturbation and you don't necessarily know what it is. But now we're going to figure out a way to solve this problem. Okay? So how are we going to solve this problem? So we're going to solve this problem the same way we solve any optimal control problem. Is first we're going to form the Hamiltonian. Which is H is L plus lambda transpose F. If I write L out, I've got 1/2 delta X transpose Q of T delta X plus, and now I've got two of these. If you see, you've got a delta X transpose MU, you got a delta U transpose M transpose delta X. So you basically get two of those, which gives you a delta X transpose times M of T times delta U. And then you've got plus 1/2 delta U transpose R of T delta U. And then you've got the last term, which is plus lambda transpose F. But lambda transpose in this case is a variation. And this gives me F of T delta X plus G of T delta U. Okay, so that's the Hamiltonian for this system. So now I need to determine the conditions, the optimality conditions for this problem. So the first thing I'm going to do is do the costate dynamics. The neighboring optimal costate dynamics are delta lambda dot is equal to minus H delta X transpose, which is equal to what? If I take the derivative, what do I get? I get minus Q of T times delta X minus M of T times delta U, and then I get minus F transpose of T times delta lambda. That gives me my perturbed costate dynamics. Now, with the boundary condition, that delta lambda at TF has to equal P at TF times delta X at TF. That comes from the fact that if you look at this cost function, if I apply the transversality conditions at the final point, I'm going to get that result right there. Or it should just be PF. Sorry. PF. Okay. Now, we also need to get the condition for the optimal control. So we know that the optimal control, or the neighboring, be careful, the neighboring optimal control is given as H delta U has to equal 0, right? So let's figure out that. And just to make life easy, let's just put a transpose on it because it doesn't change anything. So if I take H delta U transpose, it gives me M transpose of T delta X plus R of T delta U, and then plus G transpose of T delta lambda, from which we can solve for the neighboring optimal control. The neighboring optimal control is then minus R inverse times M transpose of T delta X plus G transpose of T delta lambda. So when you put all these things together, you wind up with the following systems, two differential equations in delta X and delta lambda, which is that delta X dot is going to equal F minus G R inverse M transpose times delta X minus G R inverse G transpose delta lambda, And delta lambda dot is equal to minus Q plus M R inverse M transpose times delta X, and then minus F minus G R inverse G transpose times delta lambda. So that is the system of equations that comes out of the neighboring optimal control problem that's sitting a few boards back. And you can see that now you have two boundary conditions, right? The boundary condition here is delta x at t0 equals delta x0. And the boundary condition here is delta lambda at tf is equal to pf times delta x at tf. So now let's take this one step further, okay? Which is that you should see that that problem that I have over on the board all the way to the left here, this problem should look somewhat familiar. Does this problem look at all familiar? Yeah, it looks like a linear quadratic problem, right? It's got linear dynamics. It's got a quadratic cost function. Well, what's the difference between this problem and the problem I did earlier in class? Well, it's time varying. That's true. It is time. Well, the problem I did in class was also time varying. This is time varying, but you're right. It's time varying. That one, even though yes, that one was time varying, but this is time varying. What else? What's the fundamental difference? There's one fundamental difference, and maybe you can't see it. What was the cost functional in the standard linear quadratic problem?
It did not have a mirror cost.
What's that?
It did not have a mirror cost.
It did have a mirror cost. Finite horizon problem had a mirror cost, yes. If you look back in your notes, you'll see that it did. There is a fundamental difference. What is the fundamental difference? You can't see it? What was the cost functional in the standard problem?
There is coupling between the states.
There's coupling between the state and control. Exactly. In the standard problem, the cost functional was 1/2 x transpose qx plus u transpose ru. There was no coupling between the state and the control. But you'll see that when you linearize this problem, when you linearize the dynamics and you take the second variation in that cost functional, you will, in general, get coupling between the state and the control. It's unavoidable. This is not a function of me just sticking this in there. It's a function of the fact that I have to take second derivatives with respect to x and u, and I also have to take cross derivatives, right? I have to take variation of x, variation in u. I'm not just taking second variations in x and u separately, but I also have first take variation in x and then the variation in u, and when you get that, you get this cross coupling. So if you look at the control law, you'll see that in the standard control law, what do we get? We get a minus R inverse G transpose times lambda. This is, normally we use A and B. I used F and G here, but A and B. But in this case, I've got this additional term in here. You see that? This additional term which involves this matrix M, and this matrix M is what provides that cross-coupling between those two terms. So there's an additional effect that has to be taken into account. So when you look at the state and the co-state equations on the neighboring optimal trajectory, you'll see that this matrix M keeps showing up everywhere in these. It shows up here and it shows up there, right? So you can't get around it. This is a typo. Should be sorry. So okay, now, so the way we solve this problem is, suppose we assume a solution to delta lambda of the form delta lambda is equal to p of t times delta x. So it's the same approach that we used for the standard LQ problem. We're assuming that, but remember in that case I added a beta and then we found out that beta was 0, so I'm just going to do the same thing here, except for I'm just going to assume beta is 0 without having to go through it. So if you then take the derivative, you get delta lambda dot is equal to p dot delta x plus p times delta x dot. So now let's start substituting everything in here. So what I get when I substitute is I get minus q plus m R inverse m transpose times delta x. And then minus f minus g r inverse m transpose times delta lambda. That takes care of this side. That has to equal p dot times delta x plus p times delta x dot. But delta x dot is equal to f minus g r inverse m transpose delta x, and then minus g r inverse g transpose times delta lambda. Okay. So now if I continue this substitution further, then what we get is, so we have to substitute in here for delta lambda. So then we get minus q plus m r inverse m transpose times delta x, and then minus f minus g r inverse m transpose times p times delta x, because delta lambda is equal to p times delta x. And that has to equal p dot times delta x, and then plus p f minus g r inverse m transpose times delta x. And then I've got minus p g r inverse g transpose times p times delta x. Okay. Now, you can see that all these terms now involve delta x, right? So because this last relationship must hold for all variations delta x, then all of these things must be equal to each other. So that it must be the case that minus q plus m r inverse m transpose minus f minus g r inverse m transpose times p has to equal p dot plus p times f minus g r inverse m transpose, and then minus p g r inverse g transpose p. So if you rearrange that equation, the last equation, we get p dot is equal to minus q plus m r inverse m transpose minus f minus g r inverse m transpose times p minus p times f minus g r inverse m transpose plus p g r inverse g transpose p. And then the boundary condition is that p at tf has to equal pf. And the reason that comes about is because if you take this expression, you just evaluate it at tf, you know that delta lambda at tf is equal to pf times delta x at tf, and that has to equal p at tf times delta x at tf. So p at tf has to equal pf. Okay, so what does this tell us? Okay, what's really important here, okay, is, you know, whenever you go through like a long mathematical excursion, you always have to ask yourself, well, what is this all about? So what this says is, let's suppose, so now let's get back to like when we think about the concept of actually like doing control, right? Because we're interested in doing control here, right? So I've generated a reference trajectory, I have this trajectory. I've solved some optimal control problem. It's given me a solution, a state, a control, and a co-state. I now have that. I now have that information. Now, as I start to actually execute that control, what's going to wind up happening is that there's going to be some kind of disturbance, some kind of perturbation that's going to bump me off of that optimal trajectory because my modeling's not going to be perfect. That's one thing. That there's going to be a modeling error. There could be noise in some measurement that I'm taking. There could be a disturbance being put into the system, which I did not account for when I did all this. So I'm going to get bumped off. When I get bumped off, I can do one of two things. Remember last week I told you that one of the approaches to doing this is to resolve the optimal control problem from where you are all the way to the end, right? You get bumped off, you resolve the problem, you feed that in as your new reference, and then you start from there and you go ahead and if your errors are large, that is the thing to do, because this approximation isn't going to be good if the errors are large, right? I'm only holding things to second order, so if my error is big, then that second order approximation is not going to be a very good approximation, right? So I'm assuming now that the errors are relatively small, but I still have a desire to maintain optimality, right? But I don't want to have to resolve the problem over again, because resolving it means that I have to start all over again and I've got to generate entire trajectory when I may not need to generate the entire trajectory. I may need to only just figure out the perturbation from whatever was my optimal solution and generate that trajectory, right? This is what this does for me, is it generates a trajectory that neighbors the original trajectory given the fact that I've gotten bumped off of my optimal solution by a certain amount. Now, what I'm going to do is I'm going to solve that problem. That problem is an LQ problem, as we've said, right? The LQ problem has this nice solution associated with it. It's got the solution that you need to integrate this Riccati equation backward in time from the final point back to where you are. So you get this Riccati differential equation that needs to be solved. Now, this in and of itself may require some computation to be able to do this, right? But still, I have all these matrices well defined. Everything in here is well defined because I can linearize or take the quadratic approximation of the cost, and I get all of these matrices as a function of time, and I can utilize that information to be able to help me integrate this equation backward in time. And what happens is, in the process of generating that, I wind up generating this feedback law, which allows me to be able to, did I still have it on the board? Yeah, here it is. So I generate this right here. So now let's take this next step, which is that if you then substitute the solution of that Riccati equation, let's suppose I can solve it. I substitute the solution into the optimal control, the neighboring optimal control, and I get delta U star is going to equal minus R inverse times M transpose times delta X, and then I've got plus G transpose times P times delta X, which is equal to minus R inverse times M transpose plus G transpose P times delta X. So you can see what happens here is if my perturbations are sufficiently small and I want to be able to resolve this problem, I now have a feedback law that I can use to actually solve for the neighboring optimal control. The neighboring optimal control will then be the result of solving that Riccati equation and then substituting that result in here. And given the fact that I have a perturbed state or a neighboring optimal state, I get this. So really, to be strict here, I should star. Okay. So just to be really clear, I should put a star. Okay. So what that does for me now is it generates a feedback law. So this becomes a feedback law in the neighboring optimal solution. So this is a feedback law in the neighboring optimal state delta X star of t. Now that makes some sense, right? That seems fairly reasonable, right? So what you can do now, if you think about doing this, say, on a computer, say on a digital computer, or if you're doing it, in the old days they do it on an analog computer, but if you're using it on a digital computer, what you would have is you'd have one processor that would be running that would be able to integrate this Riccati equation and solve it. And at the same time, you'd have another processor that would actually be doing the control, and it would take the solution that was computed from the from the other processor, maybe the same processor doing this, but if you want them to do it in parallel, you want the solution to the Riccati equation to be generated as quickly as possible. So you compute that. Now you have this matrix P of t. You can put that matrix P of t into the feedback law, and you can immediately generate for yourself the neighboring optimal control, which you can then feed into the system. So what does this look like? Let's see what this actually looks like in a block diagram. Okay, so this is like, getting back to basic controls when we look at a block diagram. But so what I've got here is, let's suppose here's my neighboring control, right? What does a neighboring control get multiplied by? It gets multiplied by g of t, which gets passed through to another system over here. I'll put a summer here. Now what happens is I want delta x dot. And then what I'm going to do is I'm going to pass that through an integrator, which is going to give me delta x. In order to be able to generate delta x, I need something else here. I need an input of f of t, delta x plus f of t times delta x plus g of t times delta u gives me delta x dot, right? Those are my linearized dynamics. I integrate that once, I get delta x. So now, in addition to this, I need to use this information to be able to generate for me my feedback law. So my feedback law comes in here, and I've got this big box, which includes this entire matrix here, which is that I've got minus r inverse of t times m transpose of t plus, what do I do with it? Oh, here it is. Yeah, plus g transpose of t, p of t. That's what goes in here. So remember, what's coming in here is delta x. What comes out is delta u. So there's my neighboring optimal control, right? So this gives me a way. Now, clearly, in this, somewhere in here, I need to be able to solve this Riccati equation, right? So I have to be able to integrate the Riccati equation backward in time. If there's a processor that's being used, a microprocessor that's being used to control the system to be able to do this, then the likelihood is that you probably don't want to use that processor to solve the Riccati equation too, because you probably have a limited amount of processor capability, so you want to do it with a separate processor. You have two processors, one that does one and the other one that does the other, which is what I was talking about earlier. So the nice thing about this formulation is that it has this nice elegant structure. It's a linear quadratic problem. The trouble with this formulation is as follows. You remember some of the assumptions in the linear quadratic problem. We said that in the matrices have to have certain properties associated with them. So if you remember in the linear quadratic problem, first of all, it should be, if it's not obvious, nothing's ever really obvious, so I don't like to use the word obvious. But if it's not somewhat readily apparent just from looking at these equations, you can see that everywhere in these equations, I have to take an inverse of r, right? So that means that r itself has to be invertible, right? If r is not invertible, this whole thing breaks down. But what is r? If you remember what r is equal to the second derivative of the Lagrangian evaluated at the optimal solution. So what that says is that second derivative cannot give me a singular matrix at any point along the way, otherwise my feedback law isn't going to be defined. So what we actually impose on this thing is that this thing has to be positive definite. When I say it's greater than 0, this means this matrix has to be positive definite. It cannot be positive semi-definite even. It has to be positive definite. Now, the other thing we impose, which is not strictly speaking a requirement, but it just aids in this problem being well defined, is that Q, which is equal to LXX star, we say this has to be positive semi-definite. There's no requirement on the matrix M, because M could just as well not be there, and it wouldn't affect anything. So M can have any properties it wants. In fact, M is not even a square matrix, so to say it's positive, unless the state and the control happen to be the same dimension, it's not even a square matrix. Okay, so those are a couple things. The other thing we insist on is that the pair F and G has to be controllable, Because if the system isn't controllable, it means that we cannot drive this thing back to the reference, right? That's what we're trying to do. We'd like to drive it back. We want to drive it back to the reference, right? So if we want to drive it back to the reference, we need this to be controllable. And the other thing is, in order to be able to take measurements properly, to be able to, for everything to appear in the cost, we want the pair F and Q, we want this to be an observable pair. Okay? So that is neighboring optimal control. You can actually do this yourself. You can take a problem, solve it, take the solution that you get, linearize about the optimal trajectory, approximate the cost with a quadratic by taking all these second derivatives, construct for yourself a neighboring optimal control problem, and then actually use the Riccati equation to try to integrate it backwards. And you'll see that the perturbations that you get will try to be, it's going to try to make those perturbations as small as possible, given the fact that you've been bumped off of the optimal solution by an initial amount, delta x at t0 equals delta x0. So again, this is another example of how, when you think about where this class fits into what other classes you may have taken on controls, where optimal control fits in. Optimal control can be used in two settings. It can be used as something to generate reference trajectories and controls, and that's an offline process. And then it can be used in real time or online to be able to do control. And you actually want to use the theory of optimal control, but in a somewhat simplified manner to be able to make it tractable, to be able to do perturbations from a reference solution that you've generated from some other process. So in this case, like I said, I've assumed that I've generated a reference solution from another process, and I'm going to use that reference solution as a baseline to do my perturbations, and that leads to all this neighboring optimal control stuff. Okay? So that's this part. Now, we have a couple more weeks in this class. I know that people are doing projects or thinking about projects. Not everybody has come and talked to me about their project, but I would really like people to come to my office, so just to explain to me what it is that they're planning to do, so that I can get a sense as to how complicated it is, because I really don't want, at the last minute, everyone turning in projects to me, and then they say, well, I just wasn't able to get anywhere with it because the problem was just way too complicated. If you had talked to me about it ahead of time, I could have given you some suggestions that, well, maybe that problem's not going to work out because it's too hard. And if you had simplified it, you could have gotten somewhere with it. So I would be nice if people came and talked to me about the projects, and then I can get a sense as to what everybody is doing. I don't want to tell you that you have to work on any particular problem. That's not what I'm saying. I just want it to be reasonable for the context of a project that you can get done by the end of the semester. That's all. Nothing more than that. Okay? So we'll stop here today, and also, if people have questions or they need help with things, or if nobody ever comes to my office hour, so I don't know like what people are stuck on, or if they're finding something really difficult, please, by all means, come and ask me for help. I'm more than happy to help. I'm more than happy to steer you in a different direction. I'll give you another book to read. I can do a lot of different things, but I can't do it unless you come and ask me for some help. Okay? All right. Talk to you later.